Hi everyone, I'm Esma and welcome back to the channel Q for Quantum and welcome to the lecture series, Let's Learn Quantum Computing from Scratch. So this is going to be the second lecture of this lecture series. And in today's video, we will be talking about number systems. But what we're most interested, the number systems that we're most interested in today's video are the decimal number systems and the binary number systems. So we basically want to first understand that what are number systems, and then we want to discuss a little bit of decimal number system and a little bit of binary number system. And the main thing that we want to do today is to basically see that how we can convert from a number that belongs to the decimal number system, and we want to convert it to its relevant binary form, and how we can convert the binary form back to the decimal form. So this is what we will be doing today. Today's video is going to be very mathematical sort of discussion. And it's going to be simple, not that difficult. It's going to be basic discussion today, not that difficult. So yeah, before we proceed with today's video, let's just have a brief recap of what we did in the last video. So in the last video, we talked about what exactly do we mean by information. And to understand what information is, we first try to understand the difference between data and information. We wanted to basically understand that what is the difference between data and information. This is from where we started from. So it may seem that data and information are words that have got same meaning, but that's not the case. They are completely different. They have different meanings. Data is defined as something that's unprocessed, that's unstructured, that's not organized, and that you can say that is something that is in its raw form, that is not meaningful and it's not useful. So it's something that is not in its useful form. But when you apply or when you perform some process on it, that unprocessed stuff then becomes into something that is processed in a processed form. And that processed form is what we call as information, which is meaningful and which is useful to us. Then we saw a little bit of examples. We went through a bit of examples, real life examples, to understand this difference. Then we wanted to discuss about languages so that we could understand that what is the language of a computer. So just like we humans have so many different languages that we speak, for instance, we've got English, we've got French, Japanese, Chinese, Urdu, Hindi, Spanish, so many different languages that we use to interact with one another, to communicate with one another. These languages are the ways by which we communicate, we pass on information to one another. And communication has always been one of the most important nodes of survival for the humans. And in today's world, almost everything depends upon communication. So all the languages that we use to communicate with one another, we can type them on computer. So then does that mean that the computer really understands those languages? Well, that's not the case. The computer does not understand the languages that we speak, the languages that we can actually type on it. It really does not understand those languages. It does not understand the human language. It has got its own language, which is known as the binary language. And it is the language of zeros and ones. So this is the language that computer understands, and we humans cannot understand that. So all the data that we store on our computers, that is stored in this form, in the form of zeros and ones. And why zeros and ones? So we discussed that last time. The computer is an electronic device that has got all those circuits and transistors and wires inside it. So it's an electronic device. And the way the data is stored in it is is in the form of those electric pulses, right? And electric pulses exist in two states, that's on and off. And you can call the on state as one state, or you can call it as true. You can call it as that, yes, there is an electrical signal. When there is an electrical signal, you can say yes, you can say true, you can say one. If there's no electric signal, you say zero, off, false, anything that has got two possibilities, basically. And so it is the combination of these electrical pulses, the zeros and ones, that store the data, basically. So this is what we discussed in the last video. So if you haven't watched the last video yet, you can click on the link that will appear at the top right corner of this video. You can click on that and you can watch that part. And without wasting your further time, let's proceed with today's video. So today we will be talking about the number systems. And first, we will try to understand what a number system is. And for that, let me just first hide my video. I'll stop my video now. Okay. So for that, we will use this, you can say, analogy of languages. So let's just, to understand number systems, let's just talk about languages first. So what is a language? Language is a system of communication that consists of vocabulary and grammar, right? And like we've got so many languages today, each language, whether it's English, French, German, whatever the language is, every language has its own alphabet. And alphabet is defined as a set of letters that are arranged in a particular order, and that order is a fixed order, and they represent phonemes, which is a sound or a group of sounds that is used to distinguish words. And what are letters? The elements of the alphabet are known as letters, and they're nothing but symbols that represent one or more sounds in speech. Now, let's try to understand this with an example. So let's take English language as the example. So English has its alphabet, which consists of English letters starting from A, B, C, till the letter Z. And this is the order, the fixed order in which we write them, right? And now the letters, what you do is that from the set of letters, you pick the letters and you put them in a sequence, in such a sequence that basically construct words or vocabulary, right? So you pick letters from this set, and you arrange them in an order that makes words which have meanings, which you pronounce them, you speak them, and they've got meaning. So for instance, there are a couple of examples. There's a few examples of words. You've got, for instance, when you take I and T, it makes it. When you pick, for instance, R-A-I-N, when you arrange the letters, for instance, if I pick A, I, N, and R, and then I arrange the letters in this following sequence, like first I write R, then I write A, then I write I, and then I write N, so it becomes the word rain. Then in the same way, you construct today, will, and so many words like this, you construct them. Now, when you put these words, apply the rules of English grammar to it, and you arrange these words in an order, in a particular sequence, then they construct sentences. For instance, when you rearrange it today, will, and rain, when you rearrange these words and write them in this sequence, that you first write it, then after it you write will, then after will you write rain, and then after rain you write today. So it says it will rain today, and this is the sentence. It's the sentence, and sentences are used for our communication. We use these sentences, we construct sentences that we then use to communicate with one another, either through speech or through writing. So what we just saw is that from the set of letters, you construct words, and then from words, you construct sentences that we use in our daily speech. Now, let's talk about mathematics. In mathematics, basically mathematics itself is a language, and it is a universal language. And when we say that it's a universal language, we mean that it has got like so many alphabets. It has got various alphabets, which are known as the number systems. So number system is basically a set, you can say, and each element of the set is called a digit. Just like each element of alphabet is called a letter, in the same way, each element of number system is called a digit. And these digits, like letters, are symbols, but they are used to construct numbers. And from numbers, you can then perform mathematical operations, and for instance, addition, multiplication, subtraction, division, and then you perform calculations. So there's not just one alphabet. From this, we can see that there's not just one alphabet of mathematics. There's not just one number system. There are many number systems. And here is a list of a few number systems that we have. So let's look at the first one. We have got the decimal number system, which we also call as the base 10 system. What do we mean by base? We'll just see that next. So in a while. So decimal number system is a base 10 system, and it consists of digits from 0 to 9. So it's a set of digits starting from 0 till 9. And from these digits, you pick the digits, you construct numbers, and then you perform operations on it and perform calculations, right? Then another example is the octal number system, which is the base 8 system. It starts from 0, 1, 2 till the digit 7. Then you have heptary number system, base 7, which starts from 0, ends at the digit 6. Then you have the binary number system, which we really want to look into, since we're talking about computers that use the binary language. So we are most interested in the binary number system. And it's a base 2 system, which only has 2 digits, that's the 0 and 1. Then when you go beyond base 10, like base 11, base 12, base 13, 14, 15, 16, and so on, you then encounter the number systems that have the elements that not only have digits, but they also have letters. So one of the examples is this hexadecimal number system. It's the base 16 system. It consists of digits from 0 to 9 and letters from A to F. So you construct numbers with a combination of these digits and letters. Then another such example is the vigesimal number system, which is base 20. It has digits from 0 to 9 and letters A to J. So these are just a few examples of the number systems that we have. There are many, many more, but we just listed a few of them. And out of this list, we're only going to focus on just 2 of them in our today's video, and that is the decimal number system and the binary number system. So let's just first talk a little bit about the decimal number system. So again, like we said, that it's a base 10 system. It's also called as the base 10 system, and it is a set of digits starting from 0 to 9. Now, the word base actually means the number of digits that a number system can use to express numbers. So when you're saying base 10, it means that it is a set that has got a total of 10 digits. And out of those 10 digits, you use those 10 digits and you construct numbers. So when you say base 10, it means starting from 0 till 9. If you had, let's say, base 5 system, then in that system, you would have just 5 digits. and starting from 0 till 4. Octal number system, you're going to have starting from 0 to 7, 8 digits. So it just represents the number of digits that a number system uses to express numbers. And base can be any whole number that is greater than 0. Okay. So now let's see that how we construct a decimal number, right? So here is the decimal number system, and we pick the numbers 1, 2, 5, 6, and write them down. So this actually makes a number that we usually read as 1,256, right? So it is made by the digits 1, 2, 5, and 6. Now, the value of each digit in this number, the value of each digit, is actually, it is determined by the position of that digit. So you might have learned this into elementary math classes as well. The unit digits, tens digits, 100 digits, 1,000 digits. You've gone through this in your very basic math classes. So you start from the rightmost digit, and it's called the unit digit, right? In this case, 6. In this case, 6 is the unit digit. Then you move towards the left. You have the next number 5, which holds the position of 10. So it's a 10 digit that we call. Then move a little bit more towards the left. You have 2, which is the 100 digit. And then 1 is the 1,000 digit, right? Now this unit, 10, 100, and thousands, what do we mean by that? This unit, tens, hundreds, and thousands is basically, it denotes the powers of 10. So when you're saying unit, it means to the power 0, tens means to the power 2, 100 means to the power, tens means to the power 1, 100 means to the power 2, 1,000 means to 10 to the power 3, right? So the way this number is constructed is basically like this. So if you look at 1, that's the purple digit. Since it holds the position that it's called as the 1,000 digit, so you can basically write this down as 1 times 10 to the power 3. Then you've got 2, the green digit, which holds the 100th position here, and you can write that down as 2 times 10 to the power 2. Plus, and then plus you have this 5 here, 10th digit. You write it down as 5 times 10 to the power 1. And then you have the unit digit, 6. You write it down as 6 into 10 to the power 0. In other words, you can also say that the digits 1, 2, 5, and 6, you can say, are the coefficients of this 10 to the power. For instance, this 1, you can say it's the coefficient of 10 to the power 3. You can say that this 2 is the coefficient of 10 to the power 2. You say that 5 is the coefficient of 10 to the power 1, and 6 is the coefficient of 10 to the power 0. So you have this mathematical expression in front of you. And when you solve this or simplify this further, you can then write it like this: 1,000 plus 200 plus 50 plus 6. And when you add all the numbers together, this is how you get the number 1,256, right? Now, why are we multiplying with the powers of 10 here? Because we are talking about the decimal number system, which is the base 10 number system. So for instance, if you had, let's say, an octal number system, then you would not be like multiplying it with 10 to the power 3, 10 to the power 2. You would then have 7 to the power 3, 7 to the power 2, 7 to the power 1, 7 to the power 0. Sorry, when you're talking about the octal number system, then it's the 8 to the power 3, 8 to the power 2, 8 to the power 1, and 8 to the power 0. So this 10 here is just the base. So you can say that this unit, 10, 100, and 1,000, these positions are just the powers of, they're the powers of the base, right, that you're dealing with. So that's how you're you express a decimal number system. Now this number 1256 could belong to any of the number systems, right? Any of those number systems that have all the digits 1, 2, 5, and 6. For instance, this could belong to decimal number system. It could belong to octal number system. It could belong to heptary number system. It could belong to any number system that have the digits, that have the elements 1, 2, 5, and 6. Now, to really specify that this particular number belongs to, let's say, the decimal number, what you do is that you simply represent it as in this form. You write the base of the number as the subscript. So if you're saying that this 1256 belongs to the decimal number system, you will simply write 10 at the base. And then it means that, okay, this number is from the decimal number system. If it was from the octal number system, you could write 8 here. If it was from heptary, you would write 7. So this is how you represent the numbers of belonging to some number system, right? Let's move on now to the binary number system. So binary number system, base 2 number system. By base, we mean that we mean that it has just got 2 digits with the help of which we will construct numbers. In binary number system, we have 0 and 1 as the elements. And using the combinations of zeros and ones, we construct binary numbers that belong to the binary number system. And here is a few examples of the binary numbers that we have, that we can make from this set of from this binary numbers system. Okay, now let's move on to the main part, and that is that how to convert between binary to decimal number system. So we can convert binary to any number system and vice versa. So for example, let's look at the first example where we are converting a binary number to its relevant decimal form. In this case, we have the example 1101, and we want to convert it to its decimal form. So what we do, we simply write the number here. And now since we want to convert it to its decimal form, what we will do is that we will again, just like we did previously, we mentioned the positions of each of the digits. So in the same way, you can do that. Just for your understanding, I've written this unit, 10, 100, and 1,000. So these positions here basically determine, they actually are the powers of 2. So this is the 0th position, this is the first position, this is the second, this is the third. Maybe instead of writing this units, 10, 100, 1,000, we could have written it down as 0. This rightmost digit has the position 0. Then moving to slightly towards the left, you have the position 1. Then this is the position 2, and this is the position 3. So the number of this position is basically the power of the base. I think this makes it even more clear. So instead of writing this unit 10, 100, 1,000, you can understand it in this way, that this is the 0th position, the first position, the second position, the third position. And this position 0 basically is the power of the base. And since we're talking about the binary numbers and we want to convert them to the relevant decimal form, so in this case, what we will do is we will write it like this, right? So talking about this purple digit here, purple one, so you would say 1 times 2 to the power 3. This 3 here represents the position of this 1 here. So you're starting from right to left, 0, 1, 2, 3, right? So 1 times 2 to the power 3. Then you have 1 times 2 to the power 2. Then you have 0 times 2 to the power 1. And then you have 1 times 2 to the power 0, right? So here, these digits are now the coefficients of this 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0. And then when you simplify this, it becomes 8 plus 4 plus 0 plus 1. And when you solve it, you get 13. And like this, you've converted a binary number to its decimal form. And you could do the reverse of this as well. You could like convert this decimal back to its binary form, right? And let's do that now. So now let's convert this 13 back to the binary form. How are we going to do this? Well, now what we will do is that we will divide this number 13 by 2 because we want to convert this number to the binary form. So we will be dividing 13 by 2, and we will be writing the remainders of this division in this column. So this is number 2, which is the divisor, and then this is 13, which is the dividend, and here you want to mention the remainders. So when I divide 13 by 2, I get 6. Well, actually, I don't get 6. What happens is, how we got this, so this is how you do division, right? You write 13 here, and you write 2 outside. This 13 is the dividend, this 2 is the divisor. So when you're dividing this number by 2, what you will be doing is that basically you will be recalling the table of 2. So 2 times 1, 2, 2 times 2, 4, 2 times 3, 6, 2 times 4, 8, 2 times 5, 10, 2 times 6 is 12, and 2 times 7 is 14. So since 13 is an odd number, it does not come in the table of 2. So what you do is that you cannot take 7 because 2 times 7 is 14. It's greater than 13. So what you're going to do is that you're going to take 2 times 6, which is 12. So you write 6 here. So 2 times 6, the 6 is known as the quotient. You write this quotient here, the 6 here, and you get 12, right? Now what you do is that you perform this subtraction and you get the remainder 1. So what you're doing here is that what you're doing is that when you're performing this division, you're writing the quotient here, right? And the remainder here. So 2, 6 is 12. Well, when you do 2 times 6.5, then you get 13, but you're not going to write, you can also understand it in this way, that 2 times 6.5 is equal to 13. So you're not going to write the 0.5 here, you're just going to write the whole number. So it's 6. And the remainder of that division is 1, right? Oops. Right. Now in the next step, you have the 6. Now the 6 will act as the dividend. So now you will divide the 6 by 2. And when you perform this division, you will write the results here. So when 6 is divided by 2, the result, the quotient is 3. You write the quotient here, and the remainder that you get is 0 because 6 is exactly divisible by 2. So there will be no remainders. You'll get 0. Now what you'll do in the next step, you will now divide this 3 by 2, and the quotient is 1. And the remainder you get is also 1. And now you will divide this 1 by 2, and you get 0 coefficient, and the remainder is 1, right? And you will keep on dividing this number until you get 0 here. So once you get 0 in this column, you'll stop division. You'll stop dividing. That's the end. That's where you stop. And when you look at these remainders, so these remainder, when you combine them, that forms the binary number. But how you write it down, you actually go from bottom to top. So you go in this direction. So when you perform this method, in the end, you get these remainders, and you then write them down starting from bottom to top. And when you do this, you get 1, 1, 0, 1. And this is the equivalent binary form of the number 13, right? So this is how you convert a decimal to its binary form. Now let's just look at this. So this is what we did in the last video. We also looked into this ASCII table, which is the American Standard Code for Information Interchange. This table is taken from the book Introduction to Classical and Quantum Computing by Thomas G. Wong, 2022 edition. And you can see here, we saw that these are the characters, the English language letters that you have, which are not understandable by the computer, and they're stored in this binary form. So what they've done is that you've assigned the decimal value of A. You've assigned this decimal value to A, and this is the equivalent binary form of the number 65, right? So the way you've written this binary form of this number is by performing this division, by performing this method. And the way to go back from this binary to decimal is what we discussed in the last part of this video. So yeah, that's what I wanted to show you. And yeah, this is it for today's video. This is all what we wanted to discuss. If you this was a pretty simple discussion that we had today. It was mathematical. It was quite fundamental, very basic discussion that we were having that most of you might already know. But we thought that maybe we should, I thought maybe we should have a quick revision of this. If you're someone who's interested in knowing more about number systems, this is one of the books that you can go through. You can download them from the internet. It's an amazing book, a very short book. I think it has just 46 pages that you can go through easily. It's everything is written in very simple way. So you can, in the most simplest way. So you can read this book and learn more about number systems if you want to. You can download it from the internet. And with this, yeah, so that's really it for today. I hope you guys enjoyed the video. If you did, make sure to like, share, and subscribe the channel. And do share with your friends and family, and do hit that notification bell so that whenever new videos are uploaded, you get the notification first. And I hope you understood what we did today. In the next video, we will be talking about binary number system, the binary numbers. We will be doing a little bit of that, how we perform mathematical operations on those numbers. This is what we will be discussing in the next video. So that's it for today. If you enjoyed, so make sure to like, share, and subscribe the channel. And take care of yourself. See you soon. Bye-bye.